Hello, in this video we're going to look at exponential growth and decay. So let's take a look at a little bit about structure. In general, your equations are going to look like this. So you have an output dependent on an input, and that input is the exponent to a base. Now that base, A, is either the growth or the decay factor. So they'll say things like in the problem, like something grew at a factor, and so they'll use that word, factor, of let's say 2.3 or something like that. Or they'll say it decayed by, or it decreased by a fourth. So that means you have a fourth of whatever you had before. So the idea is it's multiplication, and therefore you have an exponential function. And then the B here is just the initial population. And so if you notice, this is going to be repeated multiplication here through the exponent. Now, if you are given, so of course your base has to be greater than 1, or it has to be a fraction. It can't be 1, and of course it can't be negative. But sometimes you're given the growth rate or decay as a percent increase or decrease. And if you are, then A becomes 1 plus the rate or 1 minus the rate in the percent form. So you use a decimal form. So let's take a look at an example. So let's say here a population of fruit flies tripled every week. So they're telling you the growth rate, right? It's increasing, and how much? By a factor of 3, it tripled. So you're multiplying by 3 every week. Beginning with 20 fruit flies. So we're gonna let T be the number of fruit flies, and we're gonna let F be, T be the number of weeks, F be the number of fruit flies. So we're going to write a chart of points, graph them, and then write an equation that models this scenario. Okay. So now what happens then is, if we have here T is the input, F is the output. If you start out with at time 0, you'll notice they said you have 20 fruit flies. And then this is going to increase after 1 week. It triples, so you multiply by 3. So you're going to have 60. Then another week goes by, and you have a multiplication by 3, so 180, and so on and so forth. If you were to go out 1 more week, it gets to be a pretty big number. You multiply by 3, and you get 540. Now, if we're going to graph this, I'm not going to try to graph the 540, I don't think. That's going to be kind of hard. T, F. So let's say we go by 50s. So let's say I go 50, 100, 150, 200. And that would cover us here. Let's see if we have from here to here is 100. See, that would be 300. 500 will be way up here, 540, so I won't plot that point. But basically at 0, you're up at 20, so we'll guesstimate it. At, let's say, 1, you're up at 60, so you're just a little bit past here. At 2, you're at 180, and you can already get the feel that this thing grows very quickly, right? Very quickly, exponentially. And then the equation that models this, so this is here. The equation that models this is F as a function of T, so the number of fruit flies as a function of weeks. And you start out with 20, and then you triple, so you have 3 to the T. So notice if you multiply by 1, you had 3 to the first power. If you multiply by, if it was the second week, T is 2, you have 3 squared, right? So you multiply by 3 and 3 again, and so on and so forth. So, and also just be careful here, you can't bring the 20 into the 3. The T only applies to the 3, so you can't make this 60 to the T, okay? Okay. Let's take a look at another example. So in this case, oops, sorry about that. We have poachers have killed an alarming number of elephants, and in one forest, the population of elephants was reduced by 1/8 in 1 year, starting from 50,000 as the initial tally. So again, we're going to write a chart of points, sketch the graph, and then write an equation that models the situation. So notice what happens here is the population was reduced by an eighth. So what happens is, how much do you have left? Because that's really what happens is, you, in a sense, you're saying I want to take 50,000 and subtract an eighth to get what I have left. But what I could, an eighth of 50,000, of course, of 50,000. You could do it that way, but actually, what do we know that this is? This is like 1 times 50,000. Sorry, I'm actually supposed to factor out 50,000. And you're left times 1 minus an eighth. So really what you have is 50,000 times 7/8. Okay, so this is really what's left. That's what you want to multiply by, is what's left. So what happens then is, let's see, I've had these redone. You started out then in year 1 with the number of elephants. Well, at 0 times 0, when you first just established how many elephants there were initially, there were 50,000. And then after 1 year, you lost a seventh. So you multiply by 7/8. You lost an eighth, so what's left is 7/8. So you multiply by 7/8, and you'll get 43,750. In the second year, assuming this is going at a this is happening, the reduction is the same factor of decay. Then again, you multiply by 7/8, and you'll have 38, 28, 281. Let's just round, it's 0.25, but I'm not going to put that in there. And let's say you go to year 3, you multiply by 7/8 again, you're at 33,496 if you round it. So again, if you go ahead and plot this, here we're going to have to do like in thousands, right? So we'll have elephants in thousands. So here's 10,000, 20,000, 30,000, 40,000, 50,000. So you started out at 50,000, and then after a year, a lot was reduced. You're at 43, maybe here. In year 2, you're down to 38, so you're below 40. And in year 3, you're down to 33. So you can see this is really decaying, it's going down, right? And you can see the pattern there. So what you'll have then as your function is the number of elephants as a function of years is what you started with times 7/8 to the t. Okay. All right, let's take a look at another example. Now this is going to be an example where we're dealing with percent, and if you recall, if you have percent, you're going to look at, if it's an increase, you're going to add the rate to 1, so, because you had 100%, which is 1.0, plus whatever the rate is. That's what you're multiplying by, okay? And if you're decreasing by a certain percent, then you're multiplying by 1 minus r, okay? So here, a parking permit at a local college cost $75 last year, but the price this year increased by 9%. And we're going to assume it keeps going like that, 9%. So if we have here, T is in years, and then the parking permit, what it costs, when you start out at $75, and then what happens? You're looking at the A is 1 plus R, which is 1 plus 0.09, which is 1.09, right? So in year 1, you're going to multiply by 1.09 times 75. So you're going to have 81.75. In year 2, assuming it's growing by the same factor, right? Then you're multiplying by another 1.09. So you're going to get 89.11. And in year 3, you're going to multiply by 1.09 again. And that's going to be 97.13. And so if you were to graph this, in this case, what I would probably do is do a little double hash mark that tells someone, hey, I'm not starting at 0, and I might start here at 70, 80, 90, 100, and this is, of course, in dollars, right? So what you have, you start out at 75, 0. Then after year 1, you're at 81 something, 0.75. At year 2, you're at 89, so almost 90. Year 3, you're at 97, so you're approaching 100. So you're seeing it start to go up like an exponential. And so the parking permit as a function of the years is what you start with, $75 times 1.09 to the T. Okay. And now our last example. We have a window coating that is a window coating, and each millimeter of thickness reduces the incoming light by 5%. So if I add another millimeter, okay, so each millimeter that you add of thickness, you're going to lose another 5% of light. So how do we model this? Well, what happens is, again, with this is percent, so you're going to say 1 minus R. Now the 1 is the 100% light. So you start with 100% light. And just remember that 100% is 1.0, so you could do that too as a decimal. And what happens is you lose 5%. So what's left, you're left with 100% minus 5%, which in decimal form is 1 minus 0.05, or 0.9. Oops. That should be a 0.95. So you have 95% of whatever you had before every time you add another millimeter of thickness onto that window. So you lose 5%, you have 95% of whatever you had before of light coming in. So what happens then is, if you start graphing this, you have then for thickness, so we'll say millimeter here, and we'll say light. So we'll say at 0 millimeters, we'll have 100% light. And at 1 millimeter, we know we're going to multiply by 0.95, so we'll have 95. At 2 millimeters, we're going to multiply by 0.95 again, make sure that's 9, and then we'll have 0.9025, and 3 millimeters, multiply by 0.95 again, and you'll have 0.8574. So you can see it's going down, and so if you were going to graph this, let's say in millimeters, and light as a percent, let's see, I'd probably do the double hash mark and start maybe at 80, 90, 100, right? So if there's nothing on the window, you get 100% light. And if there's 1 millimeter on there, you get about 95%. If there's 2, you get about 90, a little over 90. And if there's 3, you get about 85 something. So you can see it coming down, right? Coming down. So now how do I represent this? Well, I can say that the light as a function of the millimeters is, start with 100 and then multiply by 0.95. Oops, I guess I'm using these, this is to the n since I'm doing millimeters. I wonder if I did that with the other ones. Just make sure. No, I used T. All right, well, that's okay. You can use whatever variable, right? So hopefully that helped you understand a little bit about exponential growth and decay. Thanks so much for listening.